Shine bright like a diamond. Shine bright like a shine bright like a diamond.
Okay. Okay, so we are not talking about Rihanna over here, we are talking about physics. Physics conversation. Today we have two students, one from Ivy League Brown and one from NYU. Introduce yourself.
Hello folks, this is Bari, Master's in Physics student at Brown University, which is in Ivy League.
And professional confuser, sine of x with a parabola.
Alright, let's get it started. Today, refraction. Do you have a better mark?
I've got a better mark.
Okay, alright, Rifat, Ivy League Brown, can you give a definition of refraction?
Yeah, n1 sine theta 1 equals n2 sine theta.
Snell's law, Bell's not law. Let's actually give a real description.
Okay, can you move a little bit this way? Okay, Isaac, yeah, give a better description of refraction.
Okay, so can I go up?
Yeah.
Alright, so when we normally talk about light, we either talk about it just moving or we talk about it reflecting perfectly off the surface. So right now it's reflecting like that with a normal line. But sometimes it will go at an angle high enough so that it no longer reflects. Instead, it refracts, which means it changes medium. It's like the light going from the air into the mirror or the water, for example. And it gets bent, so its path changes. That means its speed changes, and its wavelength changes, but its frequency does not change. And this means that theta I, the angle of incidence, is measured from the normal line, is not equal to theta R. And instead, by that bogus law Refat cited, Snell's law, we have that the index of refraction of the first material times sine of theta I is equal to the index of refraction of the second material times sine theta refracted. And this is how you will find theta refracted or theta initial given one or the other.
You made million mistakes, so stand up over here.
No.
What is the name of this one?
Well, this is the incident ray.
What is the name of this one?
That's the reflected ray.
What is the name of this one again?
That's the normal line.
What is the name of this one?
The reflected ray.
What is the angle over here?
That's the angle of incidence, as I explained.
What is the angle over here?
As I explained, that's the angle of reflection.
Oh, angle of incident is equal to angle of?
We're not talking about reflection today. We're talking about refraction.
Okay.
So this is no longer true.
So you made some mistake over here.
What did I do?
You did not write as light enters from small n to where?
To big N.
Big N. Just that theta incident is bigger than theta.
But that's not the same as saying theta is not equal to. These aren't the same. Well, of course,
this is more precise.
This one is more clarified, but this is not a mistake.
Okay, I'm going to test your understanding. Go back, because I see you're hiding some weakness.
What?
Okay, so both of you ready, right? Yeah. So let's say this is, I'm going to, Brown, is that okay if I put it down? Mm-hmm. All right, sorry, Brown. Okay, so
we don't talk about that.
All right, let's say this is air, and this is crown glass. This is diamond.
Diamond in the sky, shine bright like a diamond. Shine bright like a diamond.
Okay. Okay, so we are not talking about Rihanna over here, we are talking about physics. Okay, so a red light enters right? Okay, so a few things you're gonna find. You're gonna find theta 1, theta 2. Theta 2 is in the crown glass. Theta 3 is in the diamond. Theta 4 is in the air. Brown, can you come and construct theta 1? Can you construct theta 1?
Okay, so draw the normal line. This angle is 30, then this angle is 60 degrees. So that
Genius.
means the angle of incidence for the first
Genius.
interface is 60 degrees.
Okay, NYU, can you come?
Genius.
Can you come construct theta 2?
Okay. Can you give me the index of refraction?
Okay, I'll give you the crown glass. Crown glass N is 1.52,
1.52.
and this is N is 2.42.
2.42. Gotcha. Oh, that's pretty high. All right. So N is 1.
Oh.
Don't use your phone in class.
No, I'm calculating.
Don't use your phone in class.
Calculate.
Don't.
No,
use
you're
it in
gonna
class.
you're gonna construct it. You're gonna construct it. Do not use Snell's law. No Snell's law. Construct it.
Oh, construct it. What do you mean?
Construct it over there. If you fail, then I can call Brown.
Incompetent.
What are you saying?
You change the color from red to purple.
Yeah.
I don't have a red marker.
New physics.
Okay, right here. Is that red?
Yes, it's red enough, man.
Okay, sure. Okay. All right, I have red. No excuse.
You know what? You're an excuse.
It doesn't become brown. Come on. Just because it's going inside the glass, it doesn't become
Shine
brown.
bright like a crown glass. Shine bright like a crown glass.
All right, so find the theta. Go. Theta 2.
Okay, so I think that what we do is, please don't punish me for using Snell's law. I know I shouldn't be taking the words of a snail, but you know, we're under pressure here.
How do I put degrees?
What a stupid, what a dumb, doesn't even know how to use Desmos mobile app. Oh.
Yeah, how do I put degrees?
Okay.
Oh, I put
Arcane
degrees.
technology.
I put degrees.
It doesn't even matter whether you use degrees or radians. Shine bright like a diamond. 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 Shine bright like a diamond.
Is it 35?
34.73.
Okay, so 35.
Okay, so with that knowledge, we can now make a more accurate drawing. Listen here and listen close. I know you're a stupid man. Sorry, speaking to Refract right now.
All right. Okay. So Brown, can you construct theta 3?
Hey.
Okay.
Isaac, behave.
Okay, since it's going into another higher index material, the angle of refraction is again going to be less
That's a
than
lie.
the angle of incidence. What does it look like?
That's literally parallel. That's parallel. Broad to thinner.
No,
That's
no.
parallel.
So your normal line, you can exaggerate your normal line. Your normal line is not straight, so that's the problem.
Oh.
Yeah.
You know what? You need to sign right one.
Yeah.
That is still not
Let's make it a little bit more exaggerated.
exaggerated.
Okay.
Perfect English. How did you get your green card?
And now we can calculate. So n1 sine theta 1
This is the straightest line I've ever seen.
equals n2
Right.
sine theta 2. So n1 is crown glass, 1.52. Okay, 1.52. Theta 1 is the angle of incidence. I should mark that here. This is the angle of incidence. What is this? Well, you can see that these two are
Man discovers law of interior angles.
interior angles, right? 35 degrees. This is what we want to find, theta r. So,
Actually, by the law of
Theta
interior
one
angles, these are the same.
this is 35 degrees. That N2 is 2.42 for diamond. And we are trying to find theta 2. So
Man,
now
it's a good thing we're not doing this live.
I solve for theta 2, then I get okay. 1.52 over 2.42 sine 35, and we have to take the arc sine of this. So let me put it in the calculator. We should expect something less than 35. Let's see if that's what I get. So 1.52 over 2.42, and I have sine of 35 inside, and this gives me 20.56.
That's 21 degrees.
21.
21 degrees.
21.
And should I do the last one?
No, Isaac,
I can do that.
Isaac construct the last one. Isaac, do the construction first.
Alright, so. Put it down. Okay, so my hypothesis is that it was red.
What is your normal line?
Okay, fine. I'm gonna guess that.
What is normal line is red.
Yeah.
You have to contest the color.
Yeah.
Contest the color or contrast?
Right.
Why are you looking at the camera like? Oh.
When that, I just realized he should have the mic.
Oh, it's fine.
Does it
It's
really
fine.
matter at the end of the day? You don't want me to speak up anyway.
Okay, Isaac, you are wrong.
That's wrong.
Go.
Oh yeah, I know what's right. I know what's right. I know what's right.
That's not what he meant. It was.
Oh my god.
It's total internal reflection. It's worse. It's worse. It's like a worse form of physics.
It's wrong.
Okay. Okay. All right. Go. No, not that way. This way. This way. Isaac, come.
Oh wait, there's no bed here. No.
No, come. Okay, Raf, go. Bram, go.
So,
I've been humiliated. I'm out of here.
So it will emerge in exactly the same angle it came in.
No, that's a lie.
60 degrees.
60 degrees. Now you can imagine.
This back to the.
You can think about.
Yeah, it's back to the year.
I just realized. Oh,
Okay.
because n1 sine theta 1 is constant.
Yeah.
No, without doing.
N sine theta is constant.
Yeah.
N sine theta is constant.
No.
N1 sine theta 1 equals N2
So
sine theta 2.
you understand why it is 60?
Yes.
Okay, good.
So I have a good explanation.
No, I have a better. Okay. N1 sine theta 1 equals N2 sine theta 2 equals N3 sine theta 3 equals N4 sine theta 4. And so that means that N1 sine theta 1 equals N4 sine theta 4. But wait a second, they're the same medium, so these cancel out. So then sine theta 1 equals sine theta 4, or in other words, theta 1 equals theta 4.
No, without doing any physics, you can explain this.
How is this physics?
Without doing any math, you can explain it.
There isn't any math in here.
Go back.
Okay, we have other things to do, Brown. Okay, we are convinced that he understands it. Okay. So, some people take longer to understand. That's
So
okay.
you're telling me I'm slow.
No.
So you're telling me I'm stupid.
No, we are not.
Oh, God. Oh, you're going to get a beating off camera.
Okay. So you're gonna find velocity 1.
You are a dead man waiting.
You are velocity 1, velocity 2, velocity 3, velocity 4. Go. Find the velocity 1. You find velocity 1. You find after that you find velocity 2. Go.
Okay. So I know.
No. Right there. Exactly where I go.
No.
Put the equation.
I need to do something first. So I know that the index of refraction is defined as the ratio of the speed of light in a vacuum divided by the speed of light in a certain substance. So that means that once rearranging the equation, we get V equals C over N. So what does that mean for us? Well, that means this is just going to be C is about 3 times 10 to the 8. So then we get 3 times 10 to the 8 over 1 is 3 times 10 to the 8.
Okay, now do the next one.
No, don't remove me.
You don't have to write that.
Why are you stuck to your phone texting?
Now he's using calculator, Desmos.
That's still texting.
Okay, Isaac sit.
So
Isaac,
It's 2 times 10 to the
Isaac, pull your chair.
8. It's 2 times 10 to the 8. It's 2 times.
okay, for the next one, we have to again use the same formula. V is equal to C over N. Now C, of course, is the speed of light. Okay, just 3 times 10 to the 8. Let me write it here. And N in this case for crown glass is 1.5. And if you do
1.52.
1.52. If you do the math, you get 1.97 times 10 to the 8.
That's 2 times 10 to
2
the 8.
times 10 to the
Okay,
yeah.
2 times.
He told you so.
There's a mistake here.
Hey, you erased my units and now you're putting them back in. This guy is a crook. This
Okay.
guy is Richard Nixon.
All right. Give me B3 and B4. We said that we do not talk about U.S. president. Okay, B3.
1.24 times 10 to the 8.
B4.
3 times 10 to the 8.
He's lying.
Meters per second.
No,
It's
that's
actually
fine.
7 times 10 to the 8.
All right. Find lambda 1.
Wait, Dad, no, you made a mistake.
Where? Okay.
A physics teacher forgets to follow his own rules. Finally, I found it.
All right. Lambda 1, lambda 2, lambda 3, lambda 4. Okay. Who wants to come first?
Okay, I'll do this.
Okay.
Okay, so let me write it here. So V is equal to F lambda. Okay, in this case, V is of course C, so the speed of light because we are in air. For the first
No, B is not necessarily C.
This
Oh,
was
first
the
one.
first
Okay.
one.
Okay.
And so we know what C is, and we have to find lambda. Sorry, we have to find what? Yeah, we have to find lambda.
We know F.
Sorry, we have to
We
find
know
what?
F, yeah.
What?
So C is 3 times 10 to the 8.
And the frequency of the red light is 3.84
3.84
times 10 raised to 14.
times 10 to the 14.
Okay, Isaac, help.
This is 790.
Okay, let's use the calculator.
Nanometer. Okay, 790 nanometer is good. Isaac, do the next one.
Okay.
Okay, 2 times 10 to the
Isaac,
8.
go to the board.
Oh my goodness,
Okay,
calculator
Brian.
boy got to go on the board. Okay, so this is just 2 times 10 to the 8 over 3.84 times 10 to the 14. Another way of doing it, I suggest, is that we just divide the wavelength in air by the index of refraction.
You sure?
Yes. So
So the wavelength decrease, really?
Wavelength decrease.
Okay.
Revaps, are you stupid,
Let's
dumb,
check
brain
it.
dead, or all of the above?
Okay, go ahead.
Just check it. It slows down. That means the wavelength decreases. 520 nanometers.
Okay, next.
And then the next one is just going to be 790 over 2.42, which is 326 or 330 since we're rounding to the nearest 10. And the last one is
No, it's arrogant. Oh my god, you almost made, yeah.
You almost made up.
All right, go ahead. All right, last thing you're gonna do today, and last thing is the most difficult thing. You're gonna find F1, F2, F3, F4. Go ahead.
Sure, buddy, sure.
Go ahead, find them.
Last is most difficult
Oh,
of
you
them.
wanna go?
Yeah, I think I can do it. Oh, I've got it! I've got it! Oh, this one is so difficult. Oh, this one is so difficult too. I can't believe how difficult this is. It's literally killing me. This one, it might be the most difficult of them all, but number 4 gives you a little bit of a break. Oh man, that was so difficult. I exerted all my energy in that.
Okay. So what do we learn? We learn that the velocity.
That's impossible because 0 energy.
All right. We learned that the theta 1 is different from theta. Velocity 1 is different from. Lambda 1 is different from. What about amplitude, which we did not do?
Yeah, that stays the same.
No. Okay. What about the period?
That has to stay the same
Oh,
because
because the
frequency.
The frequency. Okay. So now, can you tell us, although angle changes, velocity changes, lambda changes, why the color stays the same?
Because frequency is the same. Color depends on frequency.
Why does frequency stay the same?
We said that many times. If lambda go up, frequency go down, so it is C.
But that's only true.
And lambda
when
go
it's
up,
constant.
lambda go down, frequency go up, so it's.
But that's only true when t is constant. When the velocity goes down, and then the wavelength goes down, we're not warranted for an increase in frequency.
Okay, Brown, why?
Yeah, so he gave a math reason, a
Yeah.
mathematical reason, but that doesn't explain why physically the frequency doesn't change. So, can I draw?
Yeah.
Picture?
Yeah.
Okay. So,
Man, this is boring.
so
You're boring.
light is like, so light is an electromagnetic wave. So what that means is that it has an electric component and a magnetic component. So here is the electric field of light, and here is the magnetic field of light. Because it's a transversal wave, the two components are perpendicular to each other at all times. So this is the magnetic component. So light is just like a rope, but that rope is electromagnetic. Now, if you think about a human standing up.
Wait, how long is this gonna be?
Just one thing.
Okay.
If you think about a human standing up and exerting a pulse, so they give a little pulse, and they send this little wave down the rope. Okay. Now let's say that over here, later on, maybe the rope is submerged into water.
How would
Okay.
the water fall out? Oh wait.
Okay, so let's say that the person is exerting this force.
No, I found a hole in your
pulse.
logic. I found a hole in your
Let
logic.
me just finish.
No, can I see and show the hole?
Can I finish?
Can I show the hole?
Yeah.
The physical pulse in the rope would be blocked by the walls of the container, so it would just splat and there
No,
would be
this
no
is-
pulse.
We're just imagining it's without it.
It's ideal scenario.
Yeah,
Okay.
Ideal,
the water
my
doesn't
deal.
come out.
It's
Okay.
two objects going through each other.
Okay.
I think
Okay.
that's broken.
Okay. Sit.
Okay.
Okay.
So you can imagine the person is making these pulses, sending these pulses down the rope
Okay.
at a certain frequency f. Okay, and then the ropes enter the submerged water, right?
Okay.
Now, when the ropes enter the water, they'll slow down, but that doesn't change at what frequency the person is creating the pulses, because the frequency is determined right here at the source where the person is creating the wave. The frequency doesn't change here. The speed of the rope changes, but not the rate at which the pulses are created. The pulses are created at the same rate because he's the one who's making the pulses. In the same way, light is an electromagnetic wave, and its frequency is determined at the source, and the source could be a laser, it can be a flashlight, it can be any kind of source that emits light. It could be a star like the sun. The frequency is determined at the source, and it doesn't matter what I put here. I can put water here.
What was the biggest thing you got out from today's lesson?
Well, actually, I got two big things out of today's lesson. Path changes, and the velocity changes, and the wavelength changes. The color doesn't change. The frequency doesn't change.
Okay, I learned that the frequency of the beam of light stays the same.